Let's dig into Module 1. For now, we're going to start with the foundation and review. And what that means is we're going to cover some materials that I assume you've had some exposure to in previous math courses, but this is just to get us all to the same footing and make sure we remember what we have already learned. So the goals of this module, of Module 1, are that we're able to describe basic entities that are used throughout computer science and throughout modern programming languages, such as booleans, numbers, sets, sequences, and functions. We'll describe some standard notation associated with those entities, and we'll be able to establish some basic shared language and terminology. It'll put us all on the same page. So why should you care about this? As a CS student, why does this concern you? Every computer science application uses basic data types. So these basic entities that I'm referring to, they're found throughout cryptography, machine learning, document retrieval, everywhere. Cryptography uses integers in important ways. Cryptography deals with the secure storage and transmission of information. This is typically based on large prime numbers, integers. Within machine learning, sets of information are clustered into non-overlapping subsets, something we'll explore. Oftentimes when you're searching for a document on your computer, you're looking through large collections based on some query. And these documents behind the scenes are sometimes represented by vectors. Vectors are a sequence of numbers, often modeled as an arrow in a specific direction. And these sequences of numbers are based on the words that are used within the document. The query also has a specific sequence of numbers representing what it's looking for, the words that are being searched for, and it's represented by a vector itself. And we find those vectors that are pointing in generally the same direction, and they'll be related documents. But behind the scenes, all of this is stored as data. And then we find functions everywhere. They're used in almost everything, from hash tables and hash functions to calculations that take place within applications, to routing of information on the internet. The possibilities are endless. Why should it concern you? Because it's embedded in everything we do. We're first going to start by exploring basic data types: Boolean values, integers, rational numbers, and real numbers. And just remind ourselves about the nomenclature used within them. Let's start off with the most basic unit of data, the bit. Bits can take either a value of 0 or 1. Every piece of information stored in a digital computer is stored as a sequence of bits. So it's always stored as a sequence of zeros and ones. And these bits, zeros and ones, can be viewed as either ones and zeros, on, off, yes, no, true, false. Boolean values were first introduced by a man named George Boole in the mid-1800s. And a Boolean value is either true or false. It contains no other option. A bit like a bit. In Java, we can use Boolean as a data type. We can hold a variable named isRaining, and we can set it equal to false. We can have a Boolean value math is fun and set that to true. Let's hope that holds. Integers are the numbers that have no fractional part. 0, the positive integers, 1, 2, 3, 4, 5, 6, 7, the negative integers, -1, -2, -3. You can see we're never going to run out of those because there's no smallest integer and there's no largest integer. There are, in fact, an infinite number of integers, which is a topic for another day. The set of all integers is represented by this double-struck Z, as you can see at the top of the screen. And that Z might seem unusual. It stands for the word numbers in German, or Zahlen. You'll note that when we represent positive integers, we sometimes write them as that double-struck Z, the Z greater than 0. So that's a superscript greater than 0, and that just represents all of those integers that are greater than 0. The same can be true for negative integers. Integers as well have a home in our modern programming languages. They're the basis for cryptography, as I mentioned. They come in many forms. Within Java, we can see them as a short, an int, a long, and as those numbers grow, they take up more space in memory, and so we try to optimize by using the smallest one that we're able to hold the number of interest. So you can see that the population of the world is going to take more space to store than, say, a 4-digit year. Real numbers, represented by that double struck R, standing for real, are all numbers that can be represented by decimal numbers, approximately. That is, all integers and all of the numbers in between them. These also have a nice home in Java, and they can be represented as floats or doubles. And these variable types can hold things like 3.967, which can't be held in an integer, an int, short or long. They can also hold things like pi. There's a math library found under java.lang.math that you'd have to import to be able to use. You can actually take a very nice approximation of pi. And I say they're held approximately represented by decimal numbers because some of these things have a non-terminating, non-repeating sequence, such as pi. There are other numbers that have a non-terminating sequence, like 0.333333 repeating, but we know that we can represent that as 1/3. And we'll see that those special cases where we can't represent that as a fraction are important. The numbers that we can represent as a fraction, so those real numbers that can be represented as a ratio or a quotient of two integers, of something of the form n over d, where n and d are both integers. D better not be 0 because we're then dividing by 0, which we know is a no-no. These numbers are called rational numbers, and they are represented by this double struck Q. And the Q stands for quotient. Rational stands for ratio. We said they can be represented as a ratio or a quotient of two numbers. Those two numbers both have names when we put them into this ratio form. When they're in the fraction, the one on top is called the numerator. The one on the bottom is called the denominator. Rational numbers absolutely have a home in our programming languages. In Java, we can store those as floats or doubles, and we can either put it in decimal format, 2.5. We know anything we can type out with a finite number of decimal places, we can represent as a fraction, or we can actually allow it to do a calculation. So anything we can create by dividing one integer by another, that's going to give us a rational number. But there are other numbers that we can't quite represent as a fraction. And these are the real numbers that are not rational. We call them irrational numbers. And they don't have their own representation, but we call that Q prime, or we represent that set of irrational numbers as Q prime. We'll see later that the square root of 2, pi, e, these are irrational numbers. We can't represent them by a fraction. And to prove that, we'll take a little bit more information, and we'll get that later. But approximations of these irrational numbers can be held in Java. And so we can, again, make use of the math library to get something close to the square root of 2. And that would be by using math.square root, that square root function of 2. And because pi is ubiquitous and necessary in many different applications, the math library has a math.pi. So note, something to keep in mind, all integers are rational numbers. Rational numbers are those numbers that we can represent as fractions. The reason that we know that's true is we can just take the integer and put a denominator of 1. So that same integer over 1, it's equal to itself. And so we know that all integers are rational numbers, but not all rational numbers are integers. Likewise, all rational numbers are real numbers, but not all real numbers are rational. And I'll show you an example of that. If we think of this large white rectangle as all of the real numbers, I've placed a few in there to point out where they can lie. So the rational numbers we can see as the blue oval, and those are numbers like 3/2, -75.94, 8 and 17/32. These are all rational numbers. We can represent them as fractions. They're also real numbers, right? They can be found on that the standard number line somewhere. The irrational numbers that we can't represent as fractions lie outside of this, like the square root of 2 and pi examples of earlier. But the integers, all of the integers lie within inside the set of rational numbers. So any integer can be represented as a fraction, and so they themselves are rational numbers. All the rational numbers are real, all the integers are rational numbers. Not all rational numbers are integers, as we see, and not all real numbers are rational. So we might need a few more symbols to keep this moving. If we want to consider all the positive integers, we've seen that we use z greater than 0, negative, we say z less than 0. We might also wish to think of the non-negative integers. So 0, 1, 2, 3, 4, 5, all of the positives plus 0, and that we can represent by saying z greater than or equal to 0. Likewise, we can do the same with non-positive integers. So all the negative integers plus 0. We can represent as z less than or equal to 0. If we want to include all integers apart from 1, if we wish to remove 0, we can refer to that as z not equal to 0, z not equal to 1 if we want all the integers aside from 1. And we can do the same with the positive real numbers, negative real numbers, etc. So, what if we want to consider a specific group within them? These are called intervals. If I want to think of all the numbers between A and B, possibly including A and B, then this is called an interval of real numbers. All the real numbers between those two specific values, those specified values are called the endpoints. If we wish to include the endpoints, we will use square brackets to represent that. If we wish to not include them, exclude those endpoints, we'll use a round parentheses to represent the fact that we're not including the endpoint. So as an example of that, if we see two round brackets around A and B, that means we want all the real numbers between A and B, but not including either A or B. And this is called the open interval between A and B. If we see square bracket A comma B, this denotes the real numbers such that they are greater than or equal to A and less than or equal to B. So everything between A and B and including both A and B at those endpoints. This is called the closed interval of B. And you can choose to include or exclude one or both of the endpoints at your leisure. Depending on whether you see a square bracket or a round parentheses, this is going to tell you whether or not that endpoint is included. And that wraps up our basic data type. Next, we'll move on to some basic mathematical notation.